Hello. Oh, Anita, I love it. Oh my God, Mimikyu. Okay, hold on. I'm just getting the board ready. We're gonna go. Second, um, some quick logistics, and then I know you can't see me yet, or can you? Yeah, okay. Some quick uh loose ends logistics, and then physics for our final hurrah. Um, Bear with me for a second. Right, that's the board. Okay. Okay. Um, so hello, yes, good afternoon. Good afternoon. Oh, we're at school. Wow, we're in a new is that where I'm not even gonna ask. Okay, good afternoon, good afternoon, everyone. All right, very good. Yes, I mean, good afternoon, Annie. Good afternoon, Vanita. Good afternoon, Mimikyu. Good afternoon, Kaya and Kayazilla. Um, uh, Charizard. Oh, here comes sorry. Good afternoon, Kaya Double. Good afternoon, Brian. Good afternoon, Genesis. Good afternoon, Vanita. Good afternoon, Sydney. Good afternoon, Natalie. Good afternoon, Carlos. Good afternoon, Mariam. Good afternoon, Annie for the double dribble. Good afternoon, Yaneli. Oh, I don't even know what that. Okay. Wow, interesting. I was curious. Okay, I'm not even sure I know. All right, I'll keep it to myself. But okay, I'm always curious. Okay, I'm not sure I know what that means though, actually. Oh, okay, got it. Thank you. Okay. Um, so hello to anybody that I didn't say hello. Yeah. Okay, Washington School. Good afternoon, direct chat person. Okay, so here is the deal. Here is the deal. Um, it's our very last class, and it's our very last. I mean, it's the last class of 204. So for many of us, it's the last class of a two-semester journey. I mean, for all of us, but you get my point. Um, I get very sentimental at the end of 204. I'll try to keep it to myself. I hope this is not the last time my path crosses with many of you. For some of you, you may hope it's the last time your path crosses with me, and that's fine. Good afternoon. Yes. Okay, got you, direct chat person. Um, Hold on one second. In fact, hold on. As long as we're hold on one second. Wait. Right. Okay. Um, One sec. Okay. Right. Okay, there's logistics, there's emotionalism, and there's physics. Um, let's get what I'm trying to say is once I get some bookkeeping things out of the way, once we make sure we're resolved on logistics, then I'm going to do physics for our last hour together. And it's the physics that gets me really excited. All of this physics gets me excited, of course, but I do view physics as a story, as a narrative. I don't mean it's false, but I mean it physics unfolds and it has a plot and it has plot twists and all of that kind of stuff. And for me, the end of 204 is like a very important beat or scene in the story of physics. I mean, it's a very conclusive scene in the story of physics that is sort of the reason that I put myself and all of you through all of 203 and 204. I mean, the other reason is it's required and you need it for your career and your majors and all that. But what I'm trying to say is that the content that I want to get to today is, to me, the exciting reward of the physics work that we've all been doing. Um, it is thick content. I will be speaking fast once I get to it in a couple of minutes. Um, it- it's content that I still think about all the time to this day, all the time. I mean, not all the time, but the content that I want to convey to you today is on my mind in one way or another, pretty in a way all the time. Um, and it doesn't get more boring for me to think about. It gets less boring for me to think about time after time after time after 30 years, which is a way of saying it's not necessarily easy content. I don't expect you to follow every detail of what I'm saying today. I don't expect you to like every detail. I don't expect you to memorize like any detail, really. I want you I want you to take a big picture, kind of relaxed view of the things I'm going to be saying in a hyper way. Um, the way I'm not expecting you, as I've said, I want you to listen once I start talking about the physics. I want you to listen for big picture themes and concepts and unifying ideas. How will I hold you accountable for these ideas, or what are you supposed to do with these ideas? Well, I remind you that if you take out one of the samples of the true false um, Google form that was used in last semester's final exam and last year's final exam, if you take that out before I start talking about the physics and you have it in front of you, it's designed to be sort of a guide as to how to listen to what I'm saying. The only way you'll be tested on what I'm saying is that way. Okay, so that's meant so that you can sort of be relaxed and see the level at which I'm asking you to absorb this. Um, okay, um, and therefore, hopefully, you can see the big concepts that I want to get across, and hopefully, you'll see them enough to want to look at them again someday, basically, to want to whatever, to look at them again in some fashion, read a book, or see a movie, look at a website, take another class, etc. Um, or come to my office and talk to me about them someday because it's what I think about all the time. Um, So that's a way of saying, even though I'm only going to get more hyper once I start talking about physics, I'm getting hyper because I have a personal need to get these ideas off of my desk and onto your desk and share them with you before I never see you again. I mean, quite frankly, it's not to make you more stressed about your exam. It's not meant for that. It's meant to give you a reason or a motivation as to why any of this stuff means anything in the first place. So hopefully you can take it in that spirit. Um, Therefore, in that spirit, again, saying that once I start talking about the physics here, I'm just gonna like go for like a solid hour. And then we'll sign off and bid each other adieu. So therefore, couple of things. Oh, sorry, and hi Ariana. Sorry, I'm looking in the chat to make sure yeah, and hi Chastity. Sorry. Um, yeah. So therefore, logistically, I'll put in the chat one more time. No, I won't. I will attempt to put in the chat one more time. Um, my cell number. So after we close down today, if any issues arise, anxiety about your grade, anxiety about the final exam, questions about my handwriting on your midterm, anything like that, I mean, I can't necessarily have the whole dialogue by text, but you can at least text me and say, I would like a 10-minute phone call or, something to allay my concerns. Or if it's a quick question, just put it in the text. But I'm saying I'm not disappearing after this class. But after this class, sort of the ball's in your court. Well, anyway, you get my point. Like I want for the next hour through it, what I'm trying to say is there's academics and there's intellectual joy. They're both important. Your success in this class, you walking away with a good grade, you walking away with a chance to get into graduate school or to your next class or a job, like all super important on it. So I don't want to leave you high and dry with any of that. If there's any concerns or anxieties that come up, reach out to me within the next week and I'll reach back and we'll address your academic or practical concerns. But then there's also just like the life of the mind. There's a reason that I do this semester after semester. Like, you get my point. And so, so I'd like you to park your academic concerns if you can once we get rolling and know that I'm here for you for them after I'm done with this little sharing session. Um, the what do I mean by the academic concerns? Just to last time, just to remind you, to hopefully it's clear, like your exam will be posted no later than 8 p.m. Friday of this week. It will be due back to me no later than 11:59 p.m. Tuesday night of next week, right? Your exam will be you'll have to solve two problems. It'll involve some kind of choice, but I'm choosing to take those two problems in any combination I want from the two documents that have been made available to you. In other words, it's some combination of the true or false may or may not appear, probably will, may or may not be a choice. I don't know. It may be obligatory, it may be optional, but the true false thing will be part of it somehow. The electric field from point charges, definitely somewhere there in the exam. Whether it's a choice or an obligation, I don't know. E flux, definitely there in the exam somewhere. Whether it's a choice or an obligation, I don't know. What was the other thing? A redo of your weaker problem from the midterm, very possibly part of the exam, very possibly a choice. Not a guarantee, no promises. I don't know for sure, but some combination of the true false, of the redo of a weaker problem from your midterm exam, flux and fields, field from point charges, all possibilities. If all possibilities, right? If you are asked to redo a problem from your midterm exam, maybe that will be mandatory. Maybe it'll be a choice. I don't know. But if it's there in your exam, if you end up redoing a problem from your midterm, well, first of all, you should check. I mean, I know that's partly because it took me so long to get them to you. I want them to be of value to you, but so you should check it out. Like if you don't understand my handwriting somewhere or something like that, you definitely check in with me. But the flip side of that is if you're redoing a problem from your midterm exam, please recognize you are redoing it from start to finish. If there's a lot of mistakes and a lot of things you have to improve, then you do all the improvements. If your problem was even if you're weaker, and you've got to submit everything so I know which your weaker problem is. I hope that's clear. I think it says it in the instructions. But if your if you rock the midterm and your weaker problem was still very, very strong and you only lost a couple of points in it, well, I mean, Quark bless America. Like I'm psyched for you. Seriously. But if you still have to do this, you still have to do it. That means you don't just hand in a correction of the one point that you got wrong. You're doing an even better draft of the very good draft that you did before. Like you're giving me a document that contains all of the beauty of your old document plus an improvement, right? So if you did really well on the midterm, yes, you may still have to you may have to spend some time recopying and moving your hand across the page and physically undergoing labor. But you should understand that if you rocked the midterm, part of the reason for this method or whatever is I don't want you going into the final exam all anxious that you're about to undo the good work that you did up until this point. That's not the purpose of the final exam. For those of you who did rock the midterm or got whatever it is that you're looking to get, then the final exam should be an opportunity for you to kind of like celebrate your success in this class and lean into it. Like seriously, if your draft was really good, then you're just embracing the quality of that draft a second time now with the confidence of knowing that it was right the first time. And that's your gift to yourself. Like, I mean, serious, like the final exam is not meant to undo people's success. What it's really meant to do is give an opportunity to those of you who didn't do as well on the midterm as you wanted or whatever. Then the final exam is an opportunity still for you to still do good. Okay, I hope that's all clear. So anyway, okay, wait. Oh. Okay, oh, did I reach it? Okay, I'm looking at the chat. I'm looking at. Okay, wait. So two things in the chat, and then I'm glad. And this, even if I'm talking hyper like I always do, this is the time to ask these questions. Like once I start, it won't be anymore. So no, I'm happy to take these questions right now. I'm going to take them one at a time. And I really do want this to be clear again because we did this anyway. One person in the direct chat, even though they said I just answered their question, which I appreciate, I still want to reiterate it. So someone said, will we be able to redo a midterm problem? Like, so what I want to make clear is it's distinctly probable. It's distinctly probable that redo a midterm problem will be part of your final exam. But I also just want to make clear that's not 100% promise. Like the 100% promise is that the only things on your final exam will be taken from the two documents you have available to you. The document, in other words, this redoing a problem for the midterm, to be totally honest, I only started doing that recently, like last semester. My jury's still out whether it's a good idea or not. It sounds like students like it, so I'm leaning in that direction, okay? But we only started doing that recently, so I'm still looking at like, was that a good idea or not? So therefore, your exam will be taken it would be any combination of problems from last semester's or last year's, and you have access to both. Okay, probably you will be asked to redo a problem from your midterm, but that's probable. It's not a definite. And also, like what I can't guarantee is whether that'll be a choice or an obligation of yours. Okay, so I want you to be prepared for anything and everything in those two documents. And the other reason I can say all this is like, well, you do need to know everything from the course. Like we need to make you need to be responsible for everything we've learned, but we don't have time to test you and grade you on everything you've learned. So this is also a way of me saying prepare for everything. And then what will be on it will be on it, but from that finite sampling of possibilities. Um, one other thing about that, and then I'm going to look back in the chat. I know. So yeah, yes, probably it will be. Probably. But that's not 100% guarantee. The other thing is, I think I mentioned this, as far as circuits are concerned, I think I mentioned, to the extent that circuits appear on your exam, that I can promise you will be a choice. You will not be required to do circuits because I never talked about it in lecture, and I know that. Okay, but some of you rock at circuits, and some of you have not only really done them in lab successfully, but I know that you've had like tutoring sessions on them, some of you, and so some of you might want to have your work on circuits rewarded, but for those of you who like never anyway, so circuits are not you get my point. Okay, wait. Now, yeah, okay, now you do like it. Okay, that's good feedback. Um, I see the feedback. Thank you. I mean, as to whether okay, great. Um, 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 um. So then there's a question: can the final exam be typed, like except for the diagrams? No, that's a really good question too. I get okay, really typed is good. Now, yes, obviously diagrams have to be diagrams. I've never meant to suggest that you have to handwrite and scan. Typing is great, or let people use tablets and stuff. You can type your exam. But the one thing I want to caution you, and in some ways, obviously, typing makes it better for you and for me. You can type your exam, someone's asking. But I would just caution you, if you like do type it in a way where you can handle typing out the equations one way or another. Like, like the equations must look like equations, whether you use math type or equation editor or LaTeX or something, Quark bless you. The equations should look right. And more specifically, if you're going to type, this is to any of you, because if you're going to type, follow the basic format of like type English, 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 whatever, whatever, whatever. Then whenever there's an equation, center the equation on its own line. It's called offsetting. Like make the equation on its own line centered, and then like the next equation, you divide both sides by two or whatever. Then the next equation offset centered, and then like English, explain the equation, English, 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 or whatever. Like don't just have big blocks of typewritten text with equations interspersed throughout English. And particularly don't do that if you, and I don't mean this about the person asking or anybody in particular, but if you're not good at doing subscripts and superscripts and you like don't know how to do symbols like pi and stuff like that, so all your equations are like all written out with carets and like that gets dangerous. It gets very hard to read and it gets very hard to follow. So if you can type, by all means, go for it, sure. And again, just remember you're trying to make this like if the typing in the end will make it a more presentable presentation and a more readable and easier to follow, then by all means. But if the typing is sacrificing colors, pictures, arrows, then then don't. But whatever makes it really, and again, you get the point. Okay. Yeah, I do prefer a fleshed out report format. Absolutely. Like, and I'm going to move on in a second. Yeah, like how you write in now I haven't seen your lab reports in a long time. I mean, I've been out of the lab for a long time, but so I haven't recently seen, but yes, I believe what I'm saying is like the way you do lab reports. That's right. To the person in the direct chat. I mean, yeah, I mean, I think you guys are getting the point at this point. I mean, some of you have had me twice. Yeah, you want your exam document to be a presentation. You want me to want to go through it. You see how long it takes me and how painstaking the grading is, and especially at this compressed time of year when there's only 1 week, like make it a document that I want to look at and that I can follow as easy and as efficiently as possible. Dazzle. So yes, if that's typing, then that means typing. Again, lastly, because the other class asked this, if there's any other questions about grading or grades or practicalities, please put them in the chat now. Just to remind you again, right? I guess I said this already, but I'm looking at the time. Oh, yeah. We got to start in a second. But the final exam is due back midnight of Tuesday. The final grades, the grading sheet with all of your data and all that will come out the next week, like in time for the grading deadline, which is Tuesday night, the 27th. In other words, Memorial Day weekend. It's always my favorite holiday. So you'll have time if someone asked this directly in another class, you will have a beat where you could see your whole grading situation and the data and the formulas and everything before it goes into CUNY first. And if there's a question or a concern on your part, yes, you have an opportunity to reach me. And of course I make mistakes. And of course I change them when I do. And of course I'd rather your grade be higher rather than lower. So if you see something that you think is wrong and too low, yes, you can and should reach out to me before it goes to CUNY first, but just reach out in peace, honestly. Reach out with a respectful question like, could you explain how you got that? Or are you sure that I never turned in block? Because I think I did. Whatever. Just please assume that I'm on your side. I'm not trying to give you a bad grade or something. Please assume that I'm invested in your success and then reach out to me in the same spirit of, I think maybe there's something you didn't see here, professor, or whatever. Like, don't start a fight because I don't want to fight. And the fight will just go sideways. Do you know what I'm saying? Like, so and I just know I'm very open to to hearing about my own mistakes and correcting them in time. It doesn't have to be a fight. You get my point. Okay. So I think that's it. Okay. So. I'm going to assume I'm going to assume that I'm going to now do physics for 50 minutes. I'm going to say one last time though, it really has been a pleasure teaching you and working with you for 1 semester in many cases, for 2 semesters in many cases. I hope you do reach out for me for help with your future, with graduate school, with et cetera, becoming a lab tech, Prism. jobs, whatever. I hope you're not a stranger. I will be in my office on Tuesday, even though I'm sure you, and for a few following Tuesdays, even though I'm sure you'll want to be gone. I will be in my office a lot more on Tuesdays next semester for what it's worth. I mean, you'll be done. But if ever you want to stop by for anything, I've rearranged things finally so that I can be much more chill and much more in my office on Tuesdays and not for what it's worth. So I would love to keep in contact with you people. You really have been a great group. Um, and you've been a great group in tough times. I mean, tough world times. And it's duly noted. And you give me hope for the future, really. Um, so that said, here we go. Just changing the view on the screen. Okay, whoop, sorry. Okay, what I want you to make it's going to come up. I want you to quickly make a note of the two value. Whoa, not of that. I did not mean to do that. All right, that's how prepared I am. Okay, just remind yourself of those two values at the top of the page. They're not, I don't want you to memorize them, but I want you to be familiar with them. Epsilon naught is the constant that always comes into all the electric field equations. It's a constant, it's just a constant of proportionality that just makes the units work out. Like it'd be a different number if we wanted to measure in different units. And originally, it's a constant that's literally experimentally inferred from late 18th century experiments with cat furs and glass rods. Like it's come from static electricity experiments, very, very specific and kind of obscure origin, but it's true, obviously. And the magnetic constant, mu naught, also a very small number, originally comes from primitive experiments. Well, not well, I mean, highly refined, but historical experiments with chunks of iron, compasses, and iron filings. Okay, and so it's that number. So you're not supposed to memorize those numbers, but you're just supposed to be aware that those two numbers just keep coming up in each one of our standard field equations. The equation underneath is what I want to get to, is the sort of the punchline of today. So we haven't said it yet. So let me remind you now what we have so far. What we have so far in the class, we've been talking about Gauss's law for a long time. Gauss's law, I'm hoping and expecting that you spent some time thinking through and that you'll spend some more time even before the final thinking through Gauss's law. You know, you had homework on it, et cetera, which I would still accept for like one more day. Um, you Gauss's law is like the centerpiece of all of this electro field analysis that we're doing. And everything, and Gauss's law again says that if you take any container throughout anywhere in space in the universe and you ask how many electrostatic field lines are fluxing out of that container, the answer will always be fully determined by the number of charge points that you find inside the container. Like, again, I'm trying to emphasize that as obscure as it all looks and as mathematical as it all looks, it's really, in a way, a straightforward idea that the stuff coming outside the boundary of a region is fully determined by whatever's inside the region. You Every charge point in the world creates a number of field lines, and you never have field lines without charge points creating them. So you want to know how many field lines are coming out of a container? Ask yourself how many charge points are inside the container. That's what Gauss's law, and then there's the I mean, that's the reasoning of or the English of Gauss's law, the first law on the top there. And then, of course, to make the units work out and everything, there's that electrostatic permittivity constant in the denominator of the right side. But the concept is number of field lines coming out is fully determined by the charge within. Now, every other law that we've developed since then, in the last week and a half, every other law has involved magnetic fields. That's like the new extra concept here. But I want you to notice, or I want to reinforce, that everything we're saying about the magnetic fields is the same type of thing that Gauss's law asked us to say. Like the consideration, the structure of our thoughts is the same when we're considering magnetic fields as they were with electric fields. It's just that the results end up being different because of this ultimate thing that magnetic fields are closed loops, are closed paths, i.e. loops, that are caused by charge flows, moving charges, whereas electric fields are lines that radiate out from static points. So notice the structure of all of these laws. And you can write down in your own notes, like the first law here in this list is Gauss's law for the electrostatic flux. The second one is Gauss's law for magnetism. The third one is Ampere's law for magnetism. And the fourth one is Faraday's law for electromagnetic induction. Like the fourth one shows a relationship between magnetic field and electrostatic field. Now, again, I know that some of these have been coming at you fast recently, but let me try again to give you the big picture of what these laws are saying. And again, let me say, if you get your mind around Gauss's law, that type of thinking is the type of thinking that's permeating all of these laws. Notice, in fact, that the left sides of all of these laws are sort of in a pattern. Like there's two laws that tell us the character or the shape of the electrostatic field, and there's two laws that tell us the character or shape of the magnetostatic, the magnetic field. Similarly, there's two laws that have to do with closed surfaces, and there's two laws that have to do with closed paths. The first two laws in this list, the two Gauss's laws, they're both have the same structure. The left side of them is a two-dimensional consideration. The right side is a three-dimensional consideration. Like in both cases of Gauss's law, it's saying, look at a closed surface. Ask yourself, if you want to know what's going on through that closed surface, all you need to know is what's happening within the volume enclosed by that closed surface, right? That's what the two first ones are saying. The next two laws are saying, look at a closed path. If you want to know what's happening in a closed path, ask yourself what's going on within the area bounded by that closed path. You see, they have the same. So the left side of any one of these laws is always asking you to look at the boundary of a region of space. And the right side is asking you to look at the region itself. The assumption is, and I've said this before, but I'm saying it again now. I always say it in slightly different words, but the assumption is well, let me back up this is the assumption, but let me back up and say quickly, regions of space can be bounded or unbounded at the same time, or independently of that, they can be closed or open. These words are related, but they're not the same. It's two different dichotomies. It's two different dichotomies. A boundary of a region is a limit or an end to that region. If you say a region of space is bounded, if you talk about the boundary of a region, you're talking about the idea that if you were navigating through that space and then you cross the boundary, you would now be in a different space. I can't put it any better than that, right? A boundary is where that space ends. Some regions are unbounded, like a line, a literal Euclidean geometric line, like goes on forever. It goes on forever. That's an unbounded one-dimensional region of space. A line segment is bounded by 2 points, et cetera, right? So regions can be unbounded or they can be bounded. But at the same time, regions can be open or closed. That's not the same thing. A line segment is bounded by 2 points, right? It's finite. Like if you're a mosquito, you could be walking along a line segment and fall. Like if you hit one of the ends, you're no longer in the line segment. But a line segment, even though it's bounded, is still open, which sounds like a contradiction or something. Maybe. If you don't know what the words mean in this context, it doesn't sound right. But a line segment is open. Why? Because it's not closed. If it were closed, it would be a circumference. It would be a ring, right? To be closed means that you could keep on walking without ever turning or changing direction. And if you were a mosquito in a region of space, if the region is closed, if you keep on walking forward without ever changing direction, you still end up where you started. That's what it means for the region to be closed. So one-dimensional regions can be closed, like a line segment can be, its edges can be touched together and it makes a ring, that's closed. Or a piece of paper, that's an area, that's a two-dimensional region. A piece of paper is open until you close it up, you touch all of its edges, and then it becomes like what English-speaking people call a surface area, right? Like the skin of a fruit is closed. A map is open, but the skin of a globe is closed, right? So regions of space can be open or closed or bounded or unbounded. And what we're tacitly realizing here is, oh yeah, when you close up a region of space, you turn it into the boundary for a higher dimensional region of space, right? When you close, and that's what Gauss's law and Ampere's law are totally sort of taking advantage of or taking into account. If you close up a surface, it becomes the boundary for an unambiguous volume within. Right, and that's how Gauss's law works. It says if you want to know all the field lines coming out of a skin, there's one and only one volume that is bounded by that skin. Just count up all the charges in that volume. So a closed two-dimensional region of space bounds a unique three-dimensional region of space. Similarly, a closed path, a ring, is the boundary for an area, a two-dimensional region of space within, like a ring. So sort of like this picture at the bottom, a ring, the blue ring is a closed path, right? It's measured in meters. Like if you were like that region of space, that blue ring is a circumference or a perimeter. It's measured in meters. It's one-dimensional, but it's bent around and now forms the boundary to an area within, right? Like the sort of the yellow circle, the yellow disc within. That disk within is an area, right? It's two-dimensional. But now notice this before I go on. Notice with how can I say this? Because we live in three dimensions, because I have access to a third dimension of space, I can tell that when I wrap a string into a ring, the area that it bounds is open, right? It's bounded, but it's open as opposed to it's not closed. It's not a surface area. It's not the skin of an orange. It's just a flat disk, right? So I can literally say a closed path bounds an open area or open surface. Same thing. I'm not, I can tell that it's open, not closed. With three dimensions, I can't do that. With the higher dimension thing, like with a three-dimensional volume, I can't tell whether it's open or closed because I don't have access to the fourth dimension of space, right? So with three dimensions, what I can tell is exactly what the shape of it is. It's unique. If you have a container, you could instantly tell the difference between what's inside the container and what's outside the container. There's no question about that. You can say that about volumes, but what we say about areas is what we say about bounded areas is that they're open. We can tell they're not closed, they're open. Okay, that's a subtle distinction in the pattern of words that I'm using here, but it's not an accident. So I'm going to get back to that. So bottom line, a closed surface bounds a unique volume, a closed path bounds an open surface. And that's what these laws about fields, that's just like statements about space. But these field statements are assuming that. So if you look at the last two, the ones about magnetism, the ones that we did the most recently, again, I'm not asking you to solve a million problems, but I'm asking you to picture them and get a feel for what these things are saying. The third one, Ampere's law, is saying, actually, I think it's drawn right here. Yeah, the third one, Ampere's law, Here's a picture of it. It's saying, look, look, look. What causes magnetism is current, is charge flow, not sitting dot of charge, but moving line of charge, right? So picture my thumb is like a current. Magnetic field lines swirl, curl around current lines because of cross products and right-hand rules and all the things that we were saying 3 days ago, and symmetry. Magnetic field lines are already closed paths. What Ampere is saying is, okay, so if you follow around the closed path, the circle of one of these magnetic lines, or sorry, if you just walk around a circle anywhere in space, the total amount of magnetism you'll pick up, the total amount of magnetic field line strength that you'll pick up is fully determined by the current enclosed by that closed path. Again, please it's new, but it's just like Gauss's law. Gauss's law said all the field lines coming out of a closed surface are fully determined by the charge within that surface. We're now saying the total magnetism around a closed line, a closed path, is fully determined by the current enclosed by that path. The only question, though, is wait a minute. I kept saying before, a closed surface bounds a unique volume. So when we say charge enclosed, whether you consciously thought about this or not, charge enclosed was sort of easier to picture. Charge enclosed meant the number of charge dots within the container that you just drew in your mind. It's easier to picture because volume is unique. Because we don't, because there's, because we live in 3 dimensions. The question here is, wait, what do I mean by current enclosed? That somehow doesn't, like, current enclosed by a ring? What current is enclosed by a ring? That doesn't seem as unambiguous. It isn't. What it means when we say current enclosed is we mean, well, remember that a closed path is the boundary to an open area? When we say current enclosed, we mean all the current passing perpendicularly through the open area bound by the closed path. So we're saying, so it's a lot of words to say something that in a way you probably were already picturing, or you could see in this picture. I'm saying if you walk around a circle in space, the total amount of magnetism that you pick up is fully determined by whatever amount of current is fluxing through, passing through, flowing through the open area, the disk, bounded by that closed path that you walked around. So you walk around, you look, what interior area did I just walk around? Oh, any current that's passing perpendicularly through that area, that's what we mean by current enclosed. So the full amount of that current times the magnetic constant will be the full amount of magnetic field around it. Okay, so that's like Gauss's law, but on a lower dimension. Similarly, Faraday's law then somehow Faraday ends up discovering that there's now a relationship, a one-way relationship between magnetism and electricity. Now notice, this is the only law that relates the two to each other right now. He says, yes, similarly, it turns out, like we didn't know, he does this apparatus that in and of itself makes sense based on the laws we already have. But then it turns out that even when you change aspects of the apparatus, unexpected, the following thing always happens, which is that if you have an open area and you change the magnetic flux through that open area, if you change the magnetic flux in time through an open area, apparently that will induce electric field in the closed path bounding that area, right? Again, same structure. I mean, I'm reading right to left when I say that. But it's the same structure of 1D boundary of a 2D region. Faraday discovered that under any conditions, no matter what you do, whether you expect it or not, if you change the magnetic flux, like in time, through an open area, that will induce electricity, electric field lines. in the closed path bounding that area. So the two laws about magnetism involve this area path thing, whereas the two final laws involve areas and their boundaries, whereas the two other laws involve volumes and their boundaries. Okay, that's what's going on here. Fine. So those a million physics laws exist, as of 1879, but those four in particular are around. And this Scottish mathematician physicist named James Clerk Maxwell, who's developing vector calculus on his own, multivariable calculus, he notices that of all these equations that are around involving electricity and magnetism, that these four have this very similar character. He starts studying the four together, sort of as a package or in relation to one another. Gauss's law for magnetism, Ampere's law, and Faraday's law. So he starts studying them, and he looks really closely at Ampere's law. And he particularly looks at it because he's applying advanced techniques of vector calculus that he's developing and playing with them mathematically and realizing that they all check mathematically according to vector calculus, except Ampere's law seems incomplete. He starts realizing that Ampere's law, which is very powerful and very compelling, it's accurate and complete if and only if we're testing or considering constant, steady currents. He notices that Ampere's law works for steady currents, but if you construct a situation where the current changes in time, then something interesting happens. So very quick, imagine a circuit that has a device in it called a capacitor. A capacitor is like two plates, two metal plates that initially have no net charge on them or anything, and they're separated by a distance or even by insulating material. So you put these two plates in a circuit, and it's called a capacitor, and it's designed to have the capacity to store charge. The purpose of the plates is that once you turn on the circuit, positive charge, starts flowing around the wires, but when positive charge hits the first plate, it lands on the first plate and sticks there. The plate is meant to catch the charge and hold on to it and not let it pass. But a voltage is still going through the whole circuit, like the battery's still working and stuff. So positive charges will start falling off the other plate and continuing around. So you start getting a buildup of positive charge on the first plate and negative charge on the second on purpose. Like this is what they're supposed to do. The purpose of a capacitor is to start storing charge, holding on to it, and create a voltage going in the opposite direction from the battery. In other words, the capacitor is designed to store charge and hold on to it so that the current slows down over time. That may seem dumb, but it's not dumb. It allows you, it allows you to start controlling the time dependence of current. It allows us to make dynamic current, and specifically any kind of timing circuit that you've ever thought of, like a circuit that turns your lights on at a certain time or keeps your oven or your VCR on for a certain amount of time. Any kind of circuits that are related to time at all have capacitors in them because capacitors allow the current to become dynamic. Okay. So Maxwell says, look, that's like a very important, like maybe Ampere, you were only concerned with steady currents, but non-steady currents are like a thing. And if you're trying to develop a law, your law, if it's meant to be a law, it should cover all cases. And he says, look at this case. There's something interesting. If I'm really thinking about space, all this regions and boundaries stuff, he says, if you look right before the capacitor, if you draw a little blue circle in your mind around the wire right before the capacitor, above at some point at the top of that circle, you see the capital letter B in blue. We would expect to find B field at the top of that circle. Anywhere around that circle, we would find B field. Right. And if we brought in a measuring tool, we would find B field in the area near that current that's going through. Right. So if you draw a circle, it seems like, you might say that your law is correct because there's B field up there. And of course, there is current passing through that circle. So fine. It sounds like Ampere's law is correct, even when the current is changing in time. But Maxwell says, but if we're really taking the geometry of all this really seriously, then you know what? We keep saying a closed surface bounds a unique volume. And we keep saying that a closed path bounds an open area. All true. We never said that the closed path bounds a unique area. Like it's open, not unique. What do I mean by that? What does Maxwell mean by that? He means this. Imagine here's a circle around the wire before the plates, the blue circle. I know it's a bad drawing. Imagine that circle. Okay, so that circle bounds an area, right? The area is like a disc, in the interior of that circle. But imagine that disc is made of rubber or latex or plastic or whatever. In other words, imagine that um, disc is made of elastic material, like a balloon that you can blow up or a glove that you can push out. So imagine now that elastic disc gets pushed out or blown up like a balloon, right? Imagine, in other words, that we blow up a balloon and we put one plate of the capacitor in the balloon. Now, this is a very obscure, weird thing, but it's motivated by high level, it's motivated by mathematical concerns that Maxwell had. But he knew they were very obscure, like math. So he then thought about it physically. And he was like, look, dude, if you blow up a balloon, the whole area of the balloon, all the plastic or rubber or whatever of that balloon, that's all one big area, right? It's not a volume. The volume is the air within the balloon, but the balloon itself is an area. And the balloon itself is an area that's bigger than when the balloon's not blown up. But it's still an area, and it's an open area. It's not closed. I mean, there's a gap in the balloon, a neck in the balloon, right, where the air came in. But that's just the point, that neck of the balloon is still the boundary for that whole area. In other words, the flat area bounded by the neck is the obvious area enclosed by the neck, but it isn't the only area bound by the neck of the balloon. You can make this bigger area that encapsulates the first plate of the capacitor, but not the second plate. And so what? You might say, so what? Well, then if we're really thinking about this law, Ampere's law, and it's really supposed to be a law, if it's supposed to be a law, that magnetic field here is determined by whatever current is passing through the area bound by the path that contains this point. Maxwell says, here's a situation where, dude, if I consider a blown up area that goes into the middle of a capacitor, then there's no current going through that area. Like all the charge is dying on the first plate on purpose. It's supposed to be. There's no charge going from the first plate to the second plate. No charge is flowing through the balloon, the skin of the balloon. No charge is flowing through the area bound by that loop. Yet there still is magnetic field at the top of that loop. So what's going on, Ampere? Now, let me pause for a second. This is very obscure, right? I mean, it's very sophisticated, very specific. It sounds like Maxwell's being a jerk. Like, what? Why are you putting a balloon in the middle of a capacitor to argue a law? Well, because, first of all, I'll tell you why. But what we're really trying to say is, look, hold on a second. There's definitely magnetic field up. If there's magnetic field up here when you look at a normal circle, there's no reason that just because in our mind we just blew up the circle and called it a balloon. Of course, that's not going to change the magnetic field up there. Like there should be magnetic field one way or the other, no matter which way we're thinking about it, right? And more specifically, what we're really saying here physically is, hang on a second. To say that there's magnetic field up there is really to say that like space knows that there's flowing charge, right? Like that there's charge flowing and the information is being conveyed in an organized fashion to space. Meaning, in other words, meaning, look, when there's a gap between two plates in a circuit, the thing is the circuit keeps working, right? I'm just trying to put this in English terms now. There's a gap between those two plates, but the circuit keeps doing its thing. Even though there's a gap between the two plates, even though no individual charges go across. And we know that. That's like the design of the circuit. So in English, in a way, what Maxwell's saying is, you know what? Like, that's the magnetic field up there represents the recognition that everything is doing what it's supposed to do. And it's doing it even though charge is not going from one plate to the other, even though current is not going through this area bound by the loop. How can we take that into account? Or how is it that the circuit, how does the world know? How does nature know that flow is supposed to be continuing even though there's a gap in the flow? And the answer is, oh, of course. If we really take all, not of course, it's not of course, but what Maxwell says is if we really take all this stuff seriously, charge, field, if we take Gauss's law seriously, Gauss's law, then what we realize, Ampere, is even though no charges are going through the skin of that balloon and making it to the other side, what is going through the skin of that balloon is electrical field lines, new electrical field, like chain, right? If charges aren't flowing, electrical field lines are. How do we know Gauss's law? The total number of field lines that come out of any surface is fully determined by the charges within that surface. So Maxwell says, you know what? I'm realizing, thinking about your law, Ampere, and I'm thinking really for magnetic field to occur up here, it could be from any combination of the contributions from actual dq/dt's, charges going across. I mean, current is dq/dt, like charges per time, right? It could be from actual charges going across, or it could be from the information caused by those charges going across, i.e., electrical flux going across. So he adds a term to Ampere's law. So he's helping Ampere. It's not really meant to be an obnoxious argument. It's meant to be an expansion of the law. And it says from now on, so there's the rewritten law. From now on, the magnetic field through a loop is a result of, yes, any standard conventional current going through the area bound by that loop, plus any flux, any electrical flux, any electrical field lines busting through the area bound by that loop, right? He adds a term called the displacement current. It's not actual current, it's not actual charges, it's the information of the charges, the electrical fields lines that are going through. If you want to see the specific math that I just did to get, I'll go back to say, like, where did I get that extra term? I just rearranged Gauss's law, literally. I just said, like, and I said that current is equal to dq/dt. Like, that is what current is, like from the lab and everything, right? I mean, it's number of charges passing by a point in space per unit time. So current is dq/dt. So what Maxwell is really saying is there doesn't seem to be any I, there doesn't seem to be any dq/dt going through that balloon skin, but there is dq/dt if by q we just rearrange Gauss's law, right? Right? Gauss's law is integral of E ds equals Q over epsilon naught. So if we just multiply both sides by epsilon naught and substitute in, then we have the d dt of that informational Q, the field lines of Q, the electrical field lines from Q rather than the Q itself. So what Maxwell is saying is now that takes care of all situations. Magnetic field here is the result of any charge going through plus any new field lines going through. That's what he's saying. Okay, so he corrects the law and adds this one term that we call the displacement current. It's like informational current. And now that covers all cases. And again, the reason Maxwell did that is because it actually mathematically works. Whatever, that's another discussion. But he wasn't trying to be obnoxious, is what I'm saying. Okay, so now we have 16 minutes left, which is good. Now again, that's a lot. But what I'm trying to say right now, I'm trying to ask you to think about regions and boundaries. And if you look through the true false thing, you'll see like, some of the questions are like reviewing old concepts that we had from early in the semester that tie into this. You'll see in a second. Nothing is meant to just be wasting your time. But then there's a lot of questions in the true false about 2-dimension, 3-dimension, 1-dimension. So just try to get your head around that. Because all these laws have this character now. What Maxwell just added to Ampere's law is a term that looks very much like the Faraday's law thing. He's saying, look, just like look at Faraday's law for a minute. Okay, I'll look at Faraday. Look at look at Faraday's law, the last one. It said if you change the magnetic flux through an open area in time, you'll get electricity through the closed path bounding that area. That was ultimately experimentally discovered. It makes sense that it would happen in certain cases, and that's why Faraday designed those cases. But then it turned out it was true in all cases, even the ones that we wouldn't have expected. So it's a law that if you change the flux, magnetic flux, through an open area, that will induce electricity in the closed path bounding that area. Now, Maxwell is saying, you know what is also true? If I study Ampere's law deeply enough and I generalize it to all cases, it also follows in a similar fashion that if you change the electric flux through an area, you'll get magnetic field in the closed path bounding that area. You see that, right? I'm saying this extra term on Ampere's law looks very much like the right side of Faraday's law, only it has a different constant. It has the constants on it, and it has a positive sign, not a negative sign. So it is a different constant, but it's a very similar concept. Okay. So what? Well, number one, well, though, so what is this with 14 minutes left? This correction on Ampere's law becomes so important. It has such implications that I'm going to try to summarize for you in the next 14 minutes. It has such vast implications, this correction, that as a result of this one term, extra term known as Maxwell's displacement current, the whole package of all these four equations then become known forever as Maxwell's equations. Like I'm saying, if you've ever heard, and you will, if you go on in STEM, you can't help but hear about Maxwell's equations, and they're like on neckties and t-shirts, like seriously. There's four of them. Sometimes they're written in a form that doesn't look like this. Sometimes they're written as derivatives, not as integrals, but whatever. These four equations that are known as Maxwell's equations, they really are Gauss's law for magnetism, Ampere's law for magnetism, and Faraday's law for electromagnetic induction. But because Maxwell corrected Ampere's law, it suddenly brought all four together into a unified package that I now want to look at with you. And the best way to look at this, and so they became known as Maxwell's equations. The best way to look at this package is to look at what it says at a point in free space, meaning let's consider just an arbitrary point in space, in a vacuum, or so arbitrary, a point in space that does not contain any charge at all or any currents, like literally free space. So I'm going to apply these four equations to a point in free space, which means anywhere I see a Q in the equations, I'm going to cross it out and call it zero. Or anywhere I see an I, I'm going to cross it out and call it zero. I'm looking at a point in free space. So Maxwell's equations, in free space become this. Like, right? So I'm saying anywhere there's a Q or an I becomes zero. So Gauss's law becomes the electric flux through a closed surface equals zero because I'm looking at free space. Like there's no charges anywhere. So I made a container. I didn't contain any charge. So there's no electric field lines. Magnetic flux was always zero, still zero through a closed surface. The closed path of electric field fully determined by Faraday's law. Faraday's law doesn't change because Faraday's law never had any Q or I in it in the first place. But now Ampere's law, the magnetic field through a closed loop, well, there's no current anymore. We're in free space. So the only magnetic field that we would find in a closed loop is fully determined by this Maxwell's displacement current, the ddt of the flux integral E dot ds. So now these are Maxwell's equations in free space. Hopefully you can see with 11 minutes left, which is fine. Hopefully you can see that something very tidy and symmetric is beginning to happen now on the right side of these equations. The left side were always a very nice package. Part of the reason that Maxwell was so interested in them is that he saw like there's a pattern in these left sides. Like these, we're really looking at two pairs of related things, but the right sides were all kind of a mess. But now that he corrected Ampere's law and applied it to free space, you can see, I think, that there's a real pattern to what's going on the right side as well. So it's very intriguing. Physicists like simplicity, beauty, patterns. So Maxwell's looking at it. He's like, all right, this is really cool. Like, it seems like the E field is related to the B field in exactly the same way in reverse, that the B field is related to the E field. Like, it looks like changes in the B field through an area cause E field. surrounding that area, and changes in the E field cause B field surrounding that area. And every time I say B field, I mean magnetic field, right? The only difference is that one of those laws seems to have a negative sign in it and one doesn't. Interesting. Okay. Oh, sorry. There's also the constants. So sorry. Hold on. I didn't mean to do that. The constants are there. Sorry. Um, so they're different by a constant, but the concept is still the same. 9 minutes. Okay. So what Maxwell, this is like really nice, but now Maxwell sees, okay, there's this really tight relationship between the E and the B, but it's so tight, it's almost frustrating because this is now like simultaneous equations or what you might call coupled equations. Like now we have this insight into this symmetry between E and B, but what it doesn't really tell, what it's not saying is what is E doing by itself that makes it related to B that way or vice versa. In other words, what Maxwell sets out to do is decouple these equations. Now, the truth is that's very hard mathematically. That is like a big math problem. And it's actually not even necessarily doable when you write the equations out in integral form. But if you do this vector calculus stuff that he was inventing on his own at the time, if you rewrite them as derivatives, as three-dimensional derivatives rather than integrals, it becomes possible to decouple them. And once he did that, once he decoupled the equations, he got he got an equation for E by itself, and he got an equation for B by itself, and they looked like this. Okay. So when he decoupled, and of course they're similar because these two are similar. When he decoupled the equations, the constants, were still involved in all of that. But he ended up getting that the second time derivative of the E field is equal to a constant times the second space derivative of the E field. And similarly, the second time derivative of the B field is equal to a constant, that constant, times the second time derivative of the B field. In other words, he got two. I mean, technically, he got these in 3 dimensions. I'm writing them in 1 dimension because that's the easier way to think about it. But he, sorry. What he got was two second order partial differential equations. Maybe I should even, I should even, I should put it like this. Might make it. I'm not changing it. Well, I am changing. He got two second order partial differential equations. Now that's pretty high level math. That's pretty obscure. And it doesn't like so, oh, great. So now I've decoupled, but I got a second order differential equation. Like, how does that help me? I mean, do I know how to solve a second order differential equation? Well, first of all, yes, Maxwell did. But more to the point, we have 7 minutes left. That is plenty of time for you to recognize, and maybe you already do, that these equations, these second order differential equations, happen to be second order differential equations that we've seen before, right? We've seen this before. Or at least we haven't seen it with E fields and B fields in it, but we've seen it with the letter Y. If in your mind, take out the letter E or the letter B and put in the letter Y, and and don't get bogged down in what the numerical value of those constants are. Just think that's a constant. You've seen this before. This is called the wave equation, right? Second time derivative of a function is equal to a constant times the second space derivative of that function. This is the wave equation, which somehow means that somehow in free space, E fields and B fields are capable of traveling as waves. Wait, what? What does now? And I know you've heard that before, but now I'm trying to show you like why we believe that you've heard of electromagnetic waves. Like, what is that all about? What it's about is this. It all goes back to the beginning of the course. What it's about is this. Say you create a current. If you just create a current that's a steady current, like doesn't change the time. Okay, current going like this will create magnetic field lines that will loop around it like that. Okay, if the current is steady, it makes steady magnetic field lines, and they're just steady, and that's it. That's fun. That's great. You've just made like a magnet, but that's the end of the discussion. no waves, nothing up my sleeve, nothing fancy about that. I mean, fancy, but nothing wild about that. But now let's take it one step further. Say you create a current that's a linear function of time, like it's growing and growing, like it's growing and growing by a same amount every second. So, like the current is like 5 times t. Okay, so the current is like 5t. It makes a magnetic field which has a strength related to 5t. But since it's growing, that means the magnetic field is changing in time, right? Like we could take a derivative of it, right? So since the magnetic field is changing, you could picture the areas, any area through any of these lines that are the area that these lines are fluxing through. The flux through that area is changing now. If the current is changing, then they are changing in time. So that will induce an electric field in the perimeter of that area, right? So now you get electric. So you have magnetic field lines looping like this. If they're changing linearly in time, then you'll get electric field lines looping around them like that. Now, if they're but if it was changing linearly, if there was one derivative, fine, then you'll get these electric fields. That's sort of cool. That's sort of interesting. But then you can't take derivatives anymore if there was only one derivative. So they're constant. So that's the end of that story, right? But you see where this is going. We have 4 minutes left. That's plenty of time for you to see where this is going. If we make a current, for example, that's, I don't know, a cosinusoidal function of time. If we make a current that allows you to take derivatives forever, if you make a current where the change of the change of the change of the change is still making a further change and no zero, then, oh my God, someone's about to, wait, oh my God, there's. Hi, how are you? I'm in the middle of a class. I'm sorry. I'm really good. Can I come back then? Yeah, sure. Please. Yeah, thanks. Oh, sorry. Okay, sorry. My God. If you make a current that is a cosinusoidal function of time, you can take derivatives of that mathematically forever, right? Which means that current will make field, B field. B field will be changing so it'll make E field at right angles to it, right? It'll make an E field around the perimeter of the area through which it is fluxing. But then that E field is changing, so it'll make a B field at right angles to it. And that will make an E field at right angles to it. And check this out, right? So you see what I'm saying? If the current is infinitely differentiable, for example, then it'll make a field, which will make a field, which will make, I mean, tons of field lines, but it'll make fields, then fields that are perpendicular to that, then fields that are perpendicular to that, then fields. And here's the catch. One of those fields has a negative sign in it. One of the laws has a negative sign. One does not, meaning that the first field you make would go according to the right-hand rule. If you're going around this way, then the field would be like that. But then the next field has a negative sign, so it won't be right-hand rule, be in effect left-hand rule. So if the first field is like this and the next field is like that, then the next field is not going to be like that. It's going to be like that. And then the next field will be like that. And then who cares? Why am I saying this? Because if they were all positive signs, then the fields would just loop around themselves and make a closed path of closed paths, and the fields would just end up where they started, whatever. But they don't. They go right, left, right, left, right, left. So the fields run out of space. They have to leave. The fields leave the things that cause them. Now that's really weird because a force is me pushing you. A field is me just pushing. Now we're talking about the push leaving the me. It literally not only doesn't have a recipient, but it doesn't have a source anymore. The fields just shoot off because they run out of space. How do they shoot off? They shoot off in the manner of a wave. The field vectors of space ripple, 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 and propagate through space in the manner of a wave. What's the speed of the wave? The square root of the constant. If you on your calculator do the square root of that constant times that constant with 1 minute left, you will find that that speed at which these fields ripple out, propagate out from their source, is the speed of light, as Maxwell found out, much to his complete shock. So what we realize from that is not only does this happen at the speed of light, but this is what light is. What light is the rate at which the electromagnetic fields of all of space update themselves. If something new happens over here, the change of information gets transmitted to over there by ripples through the field that propagate at the speed of light. Light is the rate at which the universe talks to itself. That space over here updates space over there as to what's happening. And I know it's 420. What's crazy about this, among many other things to me, is just this. Waves in the first place we believed in because they are immaterial, unthingy ripples in a medium that up until now has always been material. I can believe in water waves because it's just wiggles of water, right? But this light is wiggles and ripples through fields, and fields are not material. Fields are just raw information. So what light is informational ripples in a tank of raw information. The speed of light is the speed of universal informational update. It's the speed at which space talks to itself. That's what light is. It's the ultimate unthingy thing. It's unthingy ripples through an unthingy medium. That's the course. So you've been very, very patient. I'm going to leave. I'll see you down the line. But thank you for being so patient. Oh, great. Thank you. Okay, I'm turning off the record. But thank you. Thank you for everything. Awesome. Thank you guys. Okay, I'm turning off the. Yeah.